Welcome to Basics4AI, where mind meets machine. I'm thrilled to share with you this innovative research curriculum that makes AI accessible to young learners through games and play. Rather than diving straight into complex programming, we've created a pathway that starts with familiar activities and gradually builds conceptual understanding. Let's explore how we're reimagining AI education.
Basics4AI represents a fundamentally different approach to AI education. Instead of starting with programming or technical tools, we begin with cognitive foundations and everyday contexts. Our research shows that children aged 10 to 12 are at the perfect developmental stage to grasp these concepts when presented appropriately. We've designed a curriculum that leverages games and activities that are familiar, available, and affordable, making AI education accessible to all.
Module 1. What is AI? In our first module, we tackle the foundational question: what exactly is AI? We begin by distinguishing natural from artificial intelligence and separating simple automation from true AI. Using Russell and Norvig's framework, we introduce task environments: known, unknown, static, dynamic, fully and partially observable. Concepts that sound complex but become intuitive through our multimodal approach. Students experience these environments firsthand through maze activities, solving static paper mazes, navigating dynamic mechanical mazes, and ultimately programming maze solutions in Blockly. This progression from physical to digital builds a concrete foundation for abstract concepts. The magic of our approach lies in these engaging activities. Watch how enthusiastically students tackle both static and dynamic mazes, experiencing firsthand the difference between fully observable environments, where they can see the entire paper maze, and partially observable ones, where the mechanical maze has hidden paths. These aren't just fun games, they're carefully designed cognitive experiences that mirror how AI systems must navigate their environments. By the time students begin programming in Blockly, they've already embodied the concepts.
How AI solves problems. Module 2 builds on these foundations to explore how AI actually solves problems. We introduce the groundbreaking work of early AI pioneers through their general problem solver concepts, particularly means-end analysis. This historical perspective helps students understand that AI has been evolving for decades. The highlight is our building block activity, a hands-on supervised learning experience where students follow pictorial guided instructions to build structures. Through this tactile experience, they grasp how AI systems learn from examples and feedback. Our building block activity transforms abstract concepts into tangible experiences. Students follow guided instructions to create structures, experiencing firsthand how supervised learning works. What's remarkable is how quickly they grasp these concepts when presented in familiar contexts. We're not just teaching about AI, we're helping students recognize the AI-like thinking they already do every day. The excitement in the classroom when these connections click is absolutely palpable. In Module 3, we explore how AI makes decisions through rules-based systems and algorithms. Students discover the power of decision trees and the Minimax algorithm through the familiar game of tic-tac-toe. Our embodied activities are particularly powerful here. Students physically interact with a tic-tac-toe board, play against an AI opponent, and track the rules being applied. We then extend these concepts to a 2x2 Rubik's Cube, helping students understand what algorithms look like in different contexts before reflecting on these algorithms in relation to our earlier building block activities. These tic-tac-toe and Rubik's Cube activities generate incredible moments of insight. Students first play tic-tac-toe naturally, then play against an AI opponent, carefully tracking the rules the AI follows. When they see the Minimax algorithm in action, systematically evaluating all possible moves to find the optimal one, they often exclaim, "That's what I was trying to do." The 2x2 Rubik's Cube provides a perfect progression, showing how algorithms can be applied to different contexts while reinforcing the concepts from our building block activities.
Module 4 tackles one of the most fascinating aspects of modern AI: natural language processing. Here we explore how AI systems answer questions by making inferences based on available knowledge. Students discover the source of AI hallucinations: when systems make up information with no evidence. We also address referential ambiguity in sentences and explore how biases enter AI systems through language, human thinking, and society. Students compare outputs from Claude, Gemini, and OpenAI's models, developing critical thinking skills essential for the AI age. Students analyze comprehension passages, make evidence-based inferences, and then compare their answers to those generated by leading AI systems. The moment when they realize an AI has hallucinated information, made up facts not present in the text, is always eye-opening. Equally powerful is when they identify biases in language and recognize how these can affect AI outputs. These activities develop not just AI literacy, but critical media literacy skills essential for navigating today's information landscape. In Module 5, we explore how constraints shape problem-solving for both humans and AI. Building on experiences from the mechanical maze where holes set students back, we introduce partially completed Sudoku puzzles that demonstrate how constraints can actually help narrow possibilities. Students watch a fascinating video of a robot solving Sudoku, and then tackle a shopping cart activity, where they must optimize purchases across 3 different stores with various constraints. The shopping cart activity brings this concept into a real-world context they immediately understand. When students realize they're using the same constraint satisfaction processes as sophisticated AI systems, you can see their confidence and engagement soar. These everyday scenarios make abstract computational concepts concrete and relevant. Module 6 introduces uncertainty and risk, crucial concepts in modern AI. Through a simple yet powerful activity of drawing colored balls from a basket while blindfolded, students calculate probabilities with and without replacement. This tactile experience helps them understand how AI systems must make decisions with incomplete information. We connect back to sequential and episodic concepts from earlier modules, and students watch a self-driving car video that demonstrates how AI handles both constraints and uncertainties in high-stakes real-world scenarios. The blindfolded ball drawing activity creates genuine suspense while teaching fundamental concepts of uncertainty. Participants calculate probabilities and quickly grasp the difference between with replacement and without replacement scenarios. When we then show them self-driving cars making similar probability calculations in real time, they're amazed to see these concepts applied at such high speeds. These connections between simple games and cutting-edge technology are what make our approach so effective.
Our curriculum culminates in Module 7 with creative application projects. Students make and solve their own mazes in Scratch, applying programming skills to concepts they first encountered physically. The highlight is training an AI system to recognise hand gestures for rock, paper, scissors. Students collect training data by performing gestures, train the model, and then play against their AI creation. This full circle moment, from understanding AI concepts to actually creating AI, brings everything together in a tremendously satisfying finale.
Our research design incorporates rigorous assessment to measure both learning and engagement. We begin and end with an AI literacy cognitive inventory to measure knowledge gains. After each activity, students complete the situation motivational scale survey, and after each module, they evaluate their experience with the situational cognitive engagement scale. We conclude with semi-structured interviews to gather qualitative insights. This multifaceted assessment approach helps us understand not just what students learn, but how they engage with the material and what aspects are most effective. The significance of Basics4AI extends far beyond the classroom. By developing an accessible, engaging approach to AI education that doesn't require expensive technology or advanced teacher training, we're democratizing access to these crucial skills. As AI becomes increasingly central to society, ensuring all children have a path to AI literacy becomes not just an educational imperative, but a social justice issue. Thank you for joining me on this journey through Basics4AI. We've seen how familiar games and activities can be transformed into powerful learning experiences that build genuine understanding of AI concepts.